Hello all, welcome to the new video of Signals and Systems. In this video, we'll study about quarter wave transformer in full detail. So in the last few videos, we studied about basics of transmission lines. So first we studied about the basic parameters of transmission lines. Then we studied about how to find out the impedance at any point on transmission lines. Then we studied about the lossless transmission lines. So those are all the basics which you need to know in order to study the quarter wave transformer. So one important thing in transmission lines is to make sure that the load impedance is matching with the source impedance. So suppose say you have a transmitter with characteristic impedance Z0 and it is connected to the load RL. So if the load impedance RL is not equal to Z0, then what happens? The part of the wave or the signal will get reflected back. That is, full power will not be delivered to the load impedance RL. So in order to deliver full power to the load, we need to make sure that the load impedance is matched. So this is one of the important criteria in not only in transmission lines, in several other things as well. Okay, so matching impedance is very important to deliver full power to the load. So in all the cases, it may not be practically possible to match the load resistance with the characteristic impedance, that is of the transmitter. So there are several schemes which will help us to match the load resistance with the characteristic impedance. So one such scheme is called as quarter wave transformer. What it does is it makes sure that full power is delivered to the load and no waves are reflected back. So in this video we'll study about this in full detail. Okay, so let's start with the circuit diagram. So quarter wave transformer is a practical circuit for impedance matching. Okay, so as you can see, this is the circuit employing quarter wave transformer, and in this circuit both RL and Z0 are real and both the values are known to us beforehand. So these two are connected, as you can see, with the lambda by 4 transmission line having unknown characteristic impedance Z1 and it is of length lambda by 4, hence the name quarter wave transformer. So it is desired to match the load RL and Z0. So if you see into this lambda by 4 line, we need to make sure that the reflection coefficient is 0. So let's see how is it possible. So before that, we need to find out what is the impedance seen from this side. Okay, Zin. We need to calculate what is the value of Zin for this lambda by 4 line. So if you have seen my previous video on how to calculate impedance of a lossless line, so the final equation is this. So the impedance at any point on transmission line of a lossless transmission line looks like this. Z of L will be equal to Z0 times ZL cos beta L plus J times Z0 sin beta L, and in denominator it is Z0 cos beta L plus J times ZL sin beta L. So in that equation our characteristic impedance of the line was Z0 and load impedance was ZL. So in this case, while we are looking for input impedance from this point, we can see that the characteristic impedance is not Z0, it is Z1. Okay, and load impedance is not ZL but RL. So, and the length is given. We are seeing this is the notation is L equal to 0 here, and at any point we can calculate from here. The L is calculated from the load end. That is the notation which we have seen in the previous video as well. So here Zin is nothing but Z of lambda by 4. Okay, and Z0 is replaced by Z1 and ZL is replaced by RL. So making that changes and replacing L by lambda by 4. L equal to lambda by 4, and we know beta is equal to 2 pi by lambda. So beta L will be equal to pi by 2. Okay, so let's replace that here. So this will be cos pi by 2 or cos 90 plus j z naught sin pi by 2. So this is z1, okay, and this is z1 cos pi by 2 plus j rl sin pi by 2. So we know that cos 90 is 0 and sin 90 is 1. So this will get vanished, and this j part also will get vanished. So sin 90 is equal to 1. So the Zn will be equal to, this is Z1, okay, not Z0. So that will become, final equation will be Z1 square upon RL. Okay, so the impedance seen from this point is Z for this lambda by 4 line is Zn equal to Z1 square upon RL. Okay, so let's see in the next page. So we got the value of Zn, that is impedance looking from this side of a lossless transmission line having characteristic impedance Z1 and of length lambda by 4, which is connected to the load impedance RL is, that is Zn equal to Z1 square upon RL. So the whole point of this introducing this quarter wave transformer into this circuit is to make sure that while looking into this line lambda by 4 line, we need to make sure that the reflection coefficient is 0. So we know that this reflection coefficient will be 0 only if Zn equal to Z0. So in that case the reflection coefficient will be 0 while looking from this point. Okay, so let's put Zn equal to Z0 in this equation. In that case, so Z1 will be equal to root of Z0 RL. So what it means is, by introducing a transmission line with characteristic impedance Z1, which is square root of Z0 into RL, which both values are known to us beforehand. Okay, by introducing such line having length equal to lambda by 4, we can match the load to the characteristic impedance Z0 of the source feed. Okay, so as you can see here, there will be no reflection at this point, hence the matching will be possible. Okay, so the final conclusion is, by introducing a transmission line with impedance Z1, the value of which will be calculated using this equation, having lambda by 4 length, it is possible to match the source with the load impedance, and no power will be reflected back. So let's take one small example. Suppose we have Z0 is equal to 50 and RL is equal to 100. So since since the load impedance is not matching with the source characteristic impedance, we can make sure of this make use of this circuit. So first we need to calculate Z1, which is square root of this both. This will be 70.71. So by introducing a transmission line having characteristic impedance 70.71 having length lambda by 4, it is possible to match the characteristic impedance 50 ohm with the load impedance 100 ohms. Okay, so this is the working of quarter wave transformer. So this is just the broader perspective. Okay, so for those who are interested can watch the next part of the video, which will go in detailed analysis of this quarter wave transformer. Okay, so what we have done is we made sure that the reflection coefficient is 0 at this point, and so there will be no power reflected back. But if you are seeing the circuit for the first time, you can see that there is mismatch at this juncture. Let us say, let's call it this as first and this as second. Since 50 is not equal to 70.71, this is not matched, and since 70.71 is not matched with 100, so this is also not matched. So the common doubt arises in every student's mind, like how this quarter wave transformer is used for impedance matching, how there is no reflection back into the source field. So in order to understand that, we need to go into the detailed analysis of quarter wave transformer. So those who are interested can watch further. Otherwise, the basic understanding is enough for the most of you if you want to understand the basic working of quarter wave transformer. So let's see that the detailed analysis in the coming part. Okay. So one common doubt which arises while studying quarter wave transformer is this. So we have two interfaces, Z0 and Z1. That is, first interface is Z0 and Z1, and second interface is Z1 and RL. So neither of these two interfaces are matched. That is, impedances at neither of these two interfaces are matched. Then how quarter wave transformer is used for impedance matching? That is, how impedance matching is possible with this sort of structure. So that is the common doubt. And also, since the impedances are not matched here as well as here, there will be a reflected wave at both interfaces. That is, suppose there is a signal generator here, so it will send signal over here. Since 50 and 70.71 impedances are not matched, there will be a reflected wave here, and also some part will travel forward, and since impedances are not matched here, some part of that will go to the load and some part of will be reflected. So what happens to all this reflected waves? Why it is not, why we have not taken care of these all reflected waves is the common doubt for those who are studying quarter wave transformer. So if you go into detailed analysis of quarter wave transformer, so this doubt will be clear. So in this video, I'll try my level best to make you understand what happens to all these reflected waves and how the impedance matching is possible using quarter wave transformer. That is, uh, the proper sentence would be how impedance matching will be possible by introducing quarter wave transformer between source field and the load impedance which are not matched. Okay, so in order to understand this, we need to analyze quarter wave transformer using multiple reflection viewpoint. Okay, let me write it. So in this video, or in this part, we'll do analysis of quarter wave transformer using multiple reflection viewpoint. So this is very important for us to analyze and appreciate the design of quarter wave transformer. So let's do that. So let's see how multiple reflection viewpoint analysis is done. Okay. So let's do the analysis of quarter wave transformer using multiple reflection viewpoint. So our concern was at neither at these two interfaces, that is interface 1 and interface 2, the impedances are not matched. Then why we have not considered those reflections? There will be of course a reflected wave at this interface and reflected wave at this interface, which was not considered while discussing the quarter wave transformer, because at that time we were looking at the just broader perspective, like how quarter wave transformer will work. The detailed analysis was not done. So in order to do the detailed analysis, we need to consider this thing as well. So before going further, we need to define few parameters related to this all impedances and partial reflections which are happening in this circuit. So let's do that. The parameters which we are defining will be based on this circuit. Okay, so these are the parameters. First one is total reflection coefficient of a wave incident on quarter wave transformer. Okay, and then next one is partial reflection coefficient 1. This is nothing but reflection coefficient of a wave incident on load Z1 from Z0 line. And the next one is partial reflection coefficient 2, which is the reflection coefficient of a wave incident on load Z0 from Z1 line. And third one is the partial reflection coefficient 3, which is a reflection coefficient of a wave incident on load RL from Z1 line. And the next parameter is transmission coefficient 1. This is partial transmission coefficient 1 of a wave from Z0 to Z1 line. It means, so this is our first interface. So when a wave first encounters the interface 1, some part of the wave will be reflected back. So this partial reflection coefficient 1 will deal with that, and some of that will go further. So that is nothing but partial transmission coefficient 1. So this parameter will take care of this wave which is passed to the next interface. Okay, so similarly there is another partial transmission coefficient 2, which is of a wave from Z1 to Z0. That is, after it will get reflected here, let me draw here. So it will meet the third interface, and some of that will be reflected back, and again some of that will be reflected back again, but some of that will go ahead. So that is this, that things will be taken care by this transmission coefficient 2. So we'll understand this parameters once we use in that actual circuit. So these are all the parameters. Just go through this and it will be clear. So after understanding these parameters, now we are good to go and analyze quarter wave transformer using multiple reflection viewpoint. Okay, so I'll be doing that. I'll be using three cases and there will be a lot of equations subsequent to that. Okay, so just follow the video. Everything will be clear at the end of the video, by the end of the video. Okay, so let's analyze quarter wave transformer using multiple reflection viewpoint. So what I have done is I have represented the quarter wave transformer in terms of their impedances. Now here you can clearly see the interfaces. Okay, there is a interface 1 between Z0 and Z1, and interface 2 is between Z1 and RL. So now we are interested in finding out the total reflection coefficient. So how we do is, first we calculate all the partial reflection coefficient and then we'll sum it together. So that is our agenda right now. So let's do that. So what happens, the source sends the signal which is represented by this arrow. So first, as the signal travels through this line, it will encounter the interface 1. Now at interface 1, what it sees is, it just sees the impedance Z1 which is not matched with the impedance Z0. So part of the wave will be reflected back into the source field with the reflection coefficient 1, and some part of the wave will be sent to the next line with the transmission coefficient T1. Okay, so now we are interested only at this point. So let's say the first partial coefficient is partial reflection coefficient 1 in our first case at the interface 1. So this is the case 1. Now case 2, what happens, the some part of the wave will be reflected in this and some part will be sent to the second interface. So this is the wave. Okay, so this will travel further with the transmission coefficient 1 until it will meet the interface 2. Now again what happens, the wave sees the difference in impedance between RL and Z1. So part of the wave will be reflected back. Okay, and some part will be consumed by the load impedance RL. Now this reflection coefficient is partial reflection coefficient 3. So it will this reflected wave, what it will do, it will travel further. Okay, now what it sees, again it will sees the mismatch in impedance between Z0 and Z1 in the reverse direction. So some part of the wave will be reflected back into Z1 and some part will be transmitted to the source field Z0. Now in the case 2, we are interested only in the wave which is transmitted to the source field. So the part of the wave which is transmitted to the source field Z0 will be given by partial transmission coefficient T2. So in case 2, our overall reflection coefficient will be T1 and partial reflection coefficient 3 and T2. Since it has traveled 180 degree, there will be a negative sign. So transmission coefficient will also have same SI unit as this reflection coefficient. It is related to the voltages. So those who are interested in learning how this transmission coefficient is derived can leave the link in the description. Okay, that is not in the scope of the video. So in the case 2, we have found out the total reflections, partial reflections, as the wave traversed from say 1, 2 and 3. From 1 we will go here and we are interested in the 2, 3 and again back to 1. So this signal traversing. So what all will happen, that reflections is given by this. Okay, so let's see the third case. So let's see the case 3. Okay, so this is the third direct signal path. So this is source impedance Z0, and this is Z1 and load impedance RL. So let's calculate the total partial reflection coefficient for this signal path. So as we all know, this is T1, and some part will be reflected back, so that is given by tau 3, and some part will be reflected here, so that is given by partial reflection coefficient 2, and again partial reflection coefficient 3, and again this is given by T2. So multiplying all these paths, reflection coefficients, we have T1, T2, partial reflection coefficient 2, and partial reflection coefficient 3 square. Okay, so now totally it has traversed 180 degree here and again 180 degree here, so it will be plus sign. So this is the case 3. Now what I mean to say is, there will be infinite number of these partial reflection coefficient in the quarter wave transformer, not only limited to these 3 cases. Now again the next case will be, so you can draw the direct signal path. So the signal you can will travel into this second interface, then it will get reflected back again here, and again you can write the next direct signal path in this manner. Okay, this is the case 4. So like that there will be infinite number of this partial reflections. So if you are now we are interested to find the total reflection coefficient. So that will be nothing but this superposition of all partial reflection coefficients. That is what we have found out in case 1, case 2 plus case 3. So let's see that, and we get the generalized formula for this total reflection coefficient in a quarter wave transformer. So let's do that, then we'll get there will be a lot of equations now, so just go through that. So these are all the values of partial reflection coefficients 1, 2 and 3, and also transmission coefficient 1 and transmission coefficient 2. So the values of reflection coefficient 1, 2 and 3 are very clear. For those who are interested in this derivation, as I already told, you can see the link in the description for these two derivations. Okay, for now we'll accept these values, and then we'll proceed with the calculation of total reflection coefficient. So the total reflection coefficient is the sum of all these cases. I have calculated case 1, case 2 and case 3. So case 4 will be nothing but T1, T2, reflection coefficient 2 square, reflection coefficient 3 cube. So this we can write it as I'm just simplifying now, just check it out. So I can write it as both this reflection coefficient 2 and reflection coefficient 3, that is the product of these two, will be less than 1. So we can make use of this identity, then the summation of n is equal to 0 to 1 x of n. If x is less than 1, then the value of this will be 1 over 1 minus x. So we can make use of this equation. So in doing that, we'll get 1 over 1 minus of minus will be plus. So this is the formula for total reflection coefficient. Now we need to simplify it with the help of these and by replacing these values and all that. So I'll do this now. Let us simplify this equation. So since there is nothing to explain, I am going in the with a bit faster. So what happens? I have simplified the total reflection equation. So that will give us this values. So let's just concentrate on the numerator. Okay. So the numerator will be reflection coefficient 1 minus reflection coefficient 3, and in the bracket you can give reflection coefficient 1 square plus t1 t2. So I have calculated this value, so this will be equal to 1, what is there in the bracket, round bracket. So since then we'll end up with only reflection coefficient 1 minus reflection coefficient 3. Note that we are just dealing with the numerator of this total reflection coefficient. So after simplifying this equation, we'll end up with this, that is 2 times z1 square minus z0 rl upon z1 plus z0 and rl plus z1. So this is numerator of total reflection coefficient, which we found out by adding all those 4 cases. Okay, so this is of vital importance to us. So we know that in quarter wave transformer, we choose the characteristic impedance of the quarter wave transformer Z1 to be, so Z1 will be equal to root of Z0 into RL. So if this is the value, then only the quarter wave transformer can do impedance matching. So by substituting the value here, we'll get Z1 square will be nothing but Z0 into RL. So Z0 into RL into Z0, this will be equal to 0. Hence, the total reflection coefficient will be equal to 0. So these are all the equations which are behind this. Okay, so these all partial reflection coefficient. By adding all those partial reflection coefficients, what we got is we got the total reflection coefficient equal to 0, which means now the line is matched. So as you can see, this is possible only if we choose the characteristic impedance of quarter wave transformer to be equal to root of Z0 into RL, and also the length of quarter wave transformer should be equal to lambda by 4. So by making sure that these values are satisfied, we'll end up with total reflection coefficient equal to 0 in quarter wave transformer. Okay, so choosing that is very important. So I hope now you understand that in quarter wave transformer, superposition of all partial reflections add to 0, and hence the line will be matched. Okay, so let's see the circuit. So let's see case 3. So in quarter wave transformer, there will be reflections at interface 1 and interface 2. So these all reflections add to 0, thus making sure that the total reflection coefficient will be 0 in the steady state condition. So such that what happens, all the power will be delivered to the load RL. So this is the detailed lecture of quarter wave transformer. We have analyzed with the help of multiple reflection viewpoint. So if you have any doubts, please use the comment section. It became a bit lengthy. So those who are interested can watch this, otherwise you can watch only the half part of this video, so that is enough. So this is so after learning all these things, we can appreciate the design of many circuits. So this is one of the very beautiful circuit which you'll encounter in transmission lines. So thanks for watching the video, guys. I hope you like all our lectures. So kindly subscribe to our channel and also please spread the word. Thank you.